In this video, we'll move into section 4.7 and we'll discuss the inverse trig functions. We have to start off with a little reminder about the basics of inverse functions, that if we have an original function where f of a equals b, that the whole idea of the inverse function is to change these roles. That was the original x value a, the input in the original function f, became the output, the y, in the inverse function, and vice versa. The original y, the output in the original f function, becomes the input, or x, in the inverse function. Now, there was a little more to it, and we'll come back and remind you the only way this relationship is well defined, and that the inverse is also a function, relies on the original function being one-to-one. And unfortunately, the trig functions are going to have a little issue there. But that's the basic idea. So now when we start talking about the trig functions, we can establish that same basic relationship, but realize we know a little bit more about a and b in these circumstances. I'm not using a and b anymore because in any trig function, what we're plugging in, that idea of an input is always an angle. So I'll use a theta because that's a common symbol that we use for angles. So the input is always an angle, and then the output is some value. Now that value, depending on which way you think of it, is it one of a ratio of sides in the right triangle, right? If we're thinking about sine in the right triangle context, that value, that fraction or decimal we get, is based on the opposite over the hypotenuse. But if you think of it inside the unit circle idea, then that value is just coming as the y value from the unit circle. But either way, any way we look at it, the input is an angle and the output is some numerical value, and that those still change roles in the inverse trig relationship. Now, the notation for inverse trig, very similar to just the generic inverse function. Looks like a -1 is an exponent, but we're using that as notation for the inverse. There's also a slight alternative I will talk about here in a little bit, but mostly, our book especially, uses this inverse trig. So inverse sine, inverse cosine, inverse tangent, and that's the way that we would read it. And one more time, these roles have changed. Now the input will be the value and the output will be the angle. So we want to get used to this reverse relationship the same way we did with exponentials and logs, being able to flip back and forth. If we know sine of 30 degrees is 1/2, then we know the inverse sine of 1/2 is 30 degrees. So we still get that same back and forth relationship. Now, a couple of little tiny things before I keep going. Here I happen to use my angle in degrees. I could have done that as pi/6. It would have been exactly the same. The units on your angles don't make a difference in this context, just that the original input is an angle and then the output in the inverse trig is still an angle. Secondly, you'll notice I stuck an extra set of parentheses here. That's not a huge deal. Technically, every time we have a trig function, the angle that comes after, we always need something on the inside. Sine of x squared minus 1, sine of 30 degrees. But you always need that argument on the inside. And if that argument is simple enough, the parentheses don't hurt. I could put a parentheses around that, but it's not necessary, it's understood. And that same thing happens here, but for a lot of people, once you start getting this inverse notation, we don't want to start mixing these numbers together. So that's just a little reason why a lot of people like to have the extra parentheses here, whether this piece is simple or difficult. Okay, so that's our basics. And we've actually mentioned this a tiny bit at the very beginning of our introduction to trig. We talked about in situations where we're using the calculator. Let me use cosine for this one. If I ask you to find, and let's round to the second decimal. Another reminder, rounding directions, that means we're going to need the calculator. So if I want to find whatever this answer is, and let's do something, I don't know, let's do cosine of 49 degrees. Well, that's our standard trig button, right? We've got the angle, that's the regular trig function. So we would just think on our calculator, there's my cosine button. I would do cosine of 49. Make sure, actually I should check my mode quickly. Yep, I'm already in degree mode. So cosine of 49, done. If I'm going to round to the second decimal, look at the third. So I would get 0.66 here. But now, let's find theta And let's again get rounding directions. Let's this time go to the nearest whole degree, and we'll see it's a reverse. If I gave you something like cosine of theta equals, let's do 3/7. Fraction or decimal, that doesn't matter, right? Different situations. When we use calculators, we often get decimals here, but we've had plenty of problems by looking at right triangles or known angles that we get nice fractional relationships. But either way, it still fits the same mold. Trig function of an angle equals a value. But now look at how the problem reversed. We were given the angle and we were looking to find this value in the previous. Now we're being asked to find theta. So this is where we will use the inverse trig. Theta will be inverse cosine of 3/7, and I will do that on the calculator. I'll just do the second cosine button, 3 divided by 7. And now, again, most of the time we'd be surprised if we got a perfect nice angle. It can happen, but a lot of times we get something ugly. So again, the rounding directions to the nearest whole degree, well, 64.6 would be 65 degrees. So we've kind of already seen this a little bit. Now we get another reminder, but now we get into the deeper details. Now we got to take a little bit of a deeper look to see how this relationship is well defined and recognize that our trig functions are not one-to-one in the first place. So we're going to have to make a few little extra considerations. But just one last quick thing before I do this. You will notice as we go through, we are really going to focus on inverse sine, inverse cosine, and inverse tangent. Again, those are kind of the big three. We see those so much more. Those are the only 3 buttons you have on your calculator. But if you were asked a similar question, find theta, but you had one of the other trig functions, for instance, if you were just told to find inverse secant of 7/3, or you were told secant of theta equals 7/3, find theta, either one of these would be done the same way. If you wanted to solve this like this, you'd say, oh, I'd use inverse secant, but there is no secant button. So just as we've seen in so many of the other earlier trig ideas, when you get into the reciprocal trig functions, the key is almost always to flip it back in terms of its regular. So whether the problem started this or this, we should realize this is the same thing as this. And a lot of us, that's a little bit of a jump right off the bat. So to think of it this way, this would be some angle theta, and that's another way to express theta. And especially in this form, if we know secant is 7/3, then we know cosine is 3/7. We're a little more accustomed to knowing cosine and flipping and going to secant, but it's the same relationship. If 1 over cosine gets me to secant, well, 1 over secant gets me right back to cosine. So I could still just keep flipping. So again, everything we do from here, we're not going to get into inverse secant, inverse cosecant, or inverse cotangent, because we could turn those into problems based on sine, cosine, and tangent. Okay, last little bit about notation, then we'll get into the nitty-gritty. The last little bit on notation is, again, our book and most books use this inverse notation. So that this is how you would see inverse sine. This is how you would see inverse cosine. And that's, again, how they should be read. But you may see this, the idea of arc sine, or arc cosine, or arc tangent. It's possible, especially if, maybe some of you are using some of the alternative videos, still looking online, getting some other resources to try and help with your study. So if you see these, just to realize it's an alternative notation. This notation, the arc notation, you don't use the -1. So it just kind of cleans things up for some people a little bit, but it's the same thing. Arc sine of v, arc cosine of v, arc tangent of v, that's the same as inverse sine of v. That's the same as inverse cosine of v, inverse tangent of v. So it's just an alternative notation saying the same thing. And the last bit, we've also seen this is the common spot to put exponents. That if you see this, that is a easier way to understand, but it really means this. You're not squaring the angle. You're looking at sine of that angle and then squaring your answer. So, I mean, the Pythagorean trig identity, but other situations as well. If a trig function is squared, cubed, to any power, that's the traditional place you write it, but that's how you understand it. So it initially seems like this would be a little conflicting with that. So why does this not the same thing as this? Right? If that was a -1 exponent, that would be the same thing as 1 over sine. But this is the reason, I mean, again, first make it clear, that's not true. Again, these mean completely different things, and even putting the theta here is screwy, right? It really should be a value, not an angle. So for so many reasons, this doesn't make any sense. But why is that not a problem? It's not a problem because if we actually had sine to the -1 power, that is 1 over sine, and we've got a whole separate trig function for that. That is the definition of cosecant. So again, this is why some books prefer the arc notation, so there's no confusion with this type of idea. But our book does use it this way. This is how we have to get used to our inverse notation, and to just realize it's because of our experience we know that's not really an exponent. If it was an exponent, we'd treat it as a completely different trig function. Okay, so now let's move to our next page. And let's get a little more into the details. And let's realize right off the bat, I gave you the whole sine of 30 equals 1/2. So then we know inverse sine of 1/2 equals 30. And that's true, everybody. I didn't start you off with something that's false. That is definitely a true statement. But we have to realize the whole idea of inverses, there's a problem here. Because this is really trying to ask, what is the angle such that sine equals 1/2, right? That inverse relationship. If I want to know inverse sine of 1/2, I'm thinking of it this way. What is the angle such that sine of that angle equals 1/2? And if we think a little bit about our knowledge of trig functions, it's more than just 30 degrees. Think about the graph of sine. Right? There's my basic sine curve. High values are 1, low values are -1. I'm not going to do all the labeling as we've done before, just giving us a quick picture. Remember, just now looking at the graph, and this is the original f of x, this would be my sine x function. This function is not 1-to-1. It does not pass the horizontal line test. Horizontal lines, well, horizontal line up here, horizontal line down here, they don't hit the graph at all, but any horizontal line in here, like the x-axis or a line up here, they're going to hit the graph an infinite number of spots. So go back to this. Sine of 30 is 1/2. Yeah, that's true. There's the value 1/2, and there would be an angle of 30 degrees. So that does work, but come here. That's another spot where sine equals 1/2. And that would be 150 degrees. Keep going. Here, that's another spot where sine equals 1/2. And that would be that would be 390 degrees. Keep going. There's just more and more and more. That would be 510 degrees is 1/2 again. Come back over here. That would be, what is that? -210 degrees. So again, there's an infinite number of spots where sine equals 1/2. So what we have to do, and this is going to happen for the other two trig functions as well. This looks a little ugly in the beginning, but then after we do it, it actually works in our favor and makes our lives a little bit easier. The full domain of the sine function is -infinity to infinity. But what we are going to do, and the range would be from -1 to 1. But what I want to do, I want to cut the domain. I want to cut the domain in such a way that I still get the full range. I still get the full down to -1 up to 1, but I want to cut the graph so that it will pass the horizontal line test. Can you take a look at the picture and see where a nice spot to cut the graph might be? There are a lot of options here, but the easiest way, the conventional way to do it, is to cut the graph here to here. If I just cut the graph from here to here, this gives me the -1, and that would be negative 90 degrees. Here gives me the value of positive 1, and that would be a positive 90 degrees. If I just restrict my sine graph to those spots, this is still sine x, but now with those restrictions, now with the domain from negative 90 to 90, I still get the full range, and now I do pass the horizontal line test. So now inverse sine, f inverse of x would equal inverse sine of x. And now that is a well-defined function with a domain of negative 1 to 1 and a range from negative 90 to positive 90. I'm doing this in degrees. Of course, radians, that would be negative pi over 2 to positive pi over 2, and that would flip here as well. Again, this now all of a sudden makes our lives a lot easier. So now you're still thinking, I hope anyway, that you're thinking about this chart, this reference angle chart that we made a while back, and realize we're just using this in reverse. So let me get my sine. Remember, I'm going to just jump to the final values, 0, 1/2, rad 2 over 2, rad 3 over 2, and 1. And look how nicely this works. We used to do sine of 30 degrees is 1/2, but now we'll just do it the opposite way. We'll still go to this line even if we're doing inverse sine, but we'll start looking for the value in here and move backwards to the angle. And by the way, you could do this on your calculator as well. If you do inverse sine of 1/2 on your calculator in degree mode, your calculator will only give you one answer. The calculator is already programmed to stay in these restrictions, to only think of this in the original place so that our answers from the inverse fall in here. So let's do another one. Let's evaluate inverse sine of rad 3 over 2. There's the rad 3 over 2 matching up with sine at an angle of 60 degrees. So inverse sine of rad 3 over 2 is 60 degrees. Done. But now we have to realize another nice aspect to this, that as we look across here, everything I've given you so far are positive y values, and they're going with positive x's. So what happens if I start giving you negative y's? Well, look at the symmetry here. It'll be the same, but opposite. So in this picture up here, I had 30 degrees led me to positive 1/2. So negative 1/2 would be right here, and that would be at an angle of negative 30 degrees. All we have to do, if the value is negative, is just stick the negative on our answer. Now, again, that's a little strange because we've spent a lot of time talking about we prefer positive angles, but this is just a little exception because that's what made this graph work nicely. That was the nicest place we could have cut it. If we cut it further over here, well, we don't get negatives. If I cut it over here, well, now I'm ignoring the first 90 degrees. That's weird. So, again, let's do it again. Let's say it again. Now, if I wanted inverse sine of negative rad 2 over 2, well, once I see the negative on my value, it just becomes a negative on my answer, and the negative is done. And now from here, rad 2 over 2 connects sine with 45 degrees. So the answer is negative 45. The end. If this was inverse sine of negative rad 3 over 2, we would have got negative 60. Okay, so let's move along. And like I said, let's think about tangent and cosine as well. I'm actually going to jump to tangent next. We traditionally, sine and cosine are the primary two, but in just a moment you'll realize why I'm focusing on tangent next. So if we think about the tangent graph, we had these repeated cycles, and in plain old tangent, we had a period of 180 degrees. So we kind of looked at our typical cycle, went from negative 90, this vertical asymptote, to positive 90, this vertical asymptote. Now, the domain of tangent is not all real numbers. It's got all these vertical asymptotes that'll keep going, but the function works for all values except for those vertical asymptotes. But even with ignoring that fact, we're still in the same problem we were with sine. This does not pass the horizontal line test. So we want to do the same thing. I'm still looking at the range, which now the range goes down forever to up forever. So I'm getting negative to positive infinity. So I still want to keep the range, but I want to shrink the domain. I want to cut the domain so that the same way that what's left over still covers the same range, but that I don't have any of those horizontal line problems. Can you see where to cut the graph? It's basically the same thing we did here. The asymptotes are almost already doing our work for us. This gives me one perfectly nice cycle, so let's cut the graph from here to here. Now, the only tiny difference is that in this graph, we actually touched negative and positive 90. Those had brackets. In this one, we have the asymptotes there, so there'll be parentheses, negative 90 to positive 90. But then everything still works the same way. Now, inverse tangent is well defined. If I want inverse tangent of 1, that will be 45 degrees. Again, work on your chart a little bit, right? Fill in cosine, think about tangent. When do you do sine divided by cosine and get 1? It'll happen at 45. Sine and cosine have the same value there. Let me fill it in. Sine over cosine are the same value there. So that tangent, when I fill that in, would give me a value of 1 at 45 degrees. So tangent of 1, inverse tangent of 1 would be 45 degrees. Again, everybody, I'm sticking with degrees. If you did radians, it would just be pi over 4. That's it. Again, you want to have this idea, but the calculator still helps you if you're in trouble here. Again, we've seen some ugly values, but when we get the nice values for the functions, for the trig functions, we get the nice angles to go with them. So the calculator can definitely help a little bit here. And the same situation that we had with sine. A negative y value goes with these positive angles over here. So a negative y value will go with these negative angles over here. And once again, we have the symmetry. So that 45 degrees took me to 1. So that negative 45 degrees, oops, my picture's a little off here. So that negative 45 degrees would take me to negative 1. So inverse tan of negative 1 would just be negative 45. Okay, almost done, everybody. We still have to talk about inverse cosine, and then we have a little bit more. These restrictions still make our lives a little bit of a pain, so we just got a little bit more to get through. So page 3, let's now talk about inverse cosine. And I'll start off with the regular graph of cosine. Same idea with sine, positive 1 to negative 1 for the highs and the lows. The domain is truly everything, and the range, we only go from negative 1 to positive 1. Down to negative 1, up to positive 1, and keep doing that over and over. Well, now we run into a problem. It would be ideal to keep the same restrictions for every trig function. But if you want to cut this off from negative 90 to positive 90, well, you're not getting any of the negative values, and you're not getting rid of the horizontal line problem. You would still not pass the horizontal line test. So this last one, for cosine, we need a different restriction. So the easiest restriction for cosine will start right on the x-axis, and we'll go to here. We'll go to 180. With that restriction, now my cosine graph is just that. And now inverse cosine makes sense. I will say the book does show you the graphs of the inverse trig functions, but it's kind of like what we saw with logs, everybody. Logarithms, we did have to think a little bit about the graph. That was a common enough function to just understand a little bit of the shifting. The inverse trig functions, not so much. Most of the log work we did was about getting rid of the log and thinking in terms of exponents. Similar here, pretty much anytime we see inverse trig, we kind of want to get rid of the inverse trig and think about it in terms of the regular trig. So you could play some games with the graphs, but just knowing the shrunken version, the restricted version of the original function is enough. That goes with that. So the inverse cosine function, again, the domain and inverse would flip-flop, the domain and range, I should say. So now I'll still go from -1 to +1 for my inputs, but now I'll get 0 to 180. The positive values still work nicely with our first quadrant, with our reference angle chart. So if you were told to evaluate, let's do inverse cosine of rad 3/2. Well, that's still nice. Go back to that same chart. Now I'm looking at cosine and rad 3/2. So I'm not here, I'm here, and the angle that puts those ideas together is 30 degrees. So this answer would be 30 degrees. But here's the annoying trouble spot. From the previous ones, if I asked negative rad 3/2, well, if positive rad 3/2 went with positive 30 degrees, then negative rad 3/2 would go with negative 30, but that doesn't work with this restriction. Negative 30 is over here, and the value is still a positive rad 3/2. So now we need to stretch ourselves a little bit and realize the negative values up here are coming between 90 and 180. Realize this is all boiling down to ASTC, everybody. That sine and tangent were positive in the first quadrant and negative in the fourth, so that 0 to -90 were giving us fourth quadrant answers. And we were ignoring the second and third quadrant. Well, now with cosine, we're only thinking about quadrant 1 and quadrant 2. So this tells me that the reference angle is still 30, but I need to stick that reference angle into the second quadrant and think about the whole angle, which here would be 150 degrees. Let's do that again. Let's look at inverse cosine of negative radical 2/2. Well, positive rad 2/2 would go with 45, but negative, we'll put that 45 degrees into the reference angle in the second quadrant, and that would be my answer. 180 all the way to here, but I'm 45 degrees short of 180. That would give me 135 degrees. All right, so now let's get back to the second big part, big picture, as far as inverse functions. Initially, the idea is how we could flip these values, but the second aspect is how they cancel. That the idea of composing an inverse with an original is that they undo each other and cancel. So again, generically, that should work that if I compose a trig function with a trig inverse, or the inverse trig with the trig function, that same idea should happen. But this only happens cleanly if your value falls into these correct intervals. So let's do a few of these. This, I have to be honest, everybody, this is an annoying, nitpicky section. It doesn't come up all that often, but especially for those who go to calculus and then Calc 2, these ideas come up all over again. So it's something we want to focus on. It's certainly a spot we're so accustomed to just canceling and getting x, but that extra thought, would that x fall in the right intervals? So let's evaluate several of these. Let's start number 1. Let's go sine of sine inverse of 3/4. Well, the inverse sine is the inner part. Does 3/4, does that as a value make sense with sine? Well, sine is never bigger than 1 or lower than -1. So if that was inverse sine of 4/3, that would be undefined. And then we can't keep going. So that would be a spot they wouldn't cancel. The answer would just be error, undefined. But since the 3/4 is viable, that is between -1 and 1, these do cancel, and there's your answer. Similarly, let's do that the other way. Let's go inverse cosine of cosine of, let's do 15 degrees. Same idea. It's so tempting to just cross these off and say 15 degrees, but just take one moment. Does 15 degrees make sense in inverse cosine? And it does. The restriction for cosine was 0 to 180, and that falls in that interval. So this again cancels and would just give me the 15 degrees. So now let's see two that don't work quite as nicely. These two, we tried to look for the catches, but to realize that everything worked nice and neat. So now when I do number 3, now let's stick with cosine for a moment. Let's go cosine of inverse cosine of -2. Again, so tempting to just cross these off and say -2, but this makes no sense. What is the angle such that cosine equals -2? Well, cosine only goes up to 1 and down to -1. It never gets down to -2. So this is either an undefined or it does not exist. If you try and type this in your calculator, and by the way, another spot, there are a lot of people that they really get through this section leaning heavily on their calculator, but I just want to warn you, if you're going to go forward, eventually, again, the Calc 2 people, several classes down the road, but the Calc 2 people, you have to be able to do this stuff generically with variables, and the calculators can't help you there. So again, it's a good time to try. Use the calculator as a backup, okay? And if you do both of these in your calculator, well, as long as you're in degree mode, that works fine. That doesn't matter what mode, that'll work out cleanly. I think most calculators will give you some sort of an error message here, so that's kind of a hint for the does not exist. But now, number 4, let's do inverse sine of 115 degrees. Now, you put this in your calculator, you do not get 115. It's not an error. 115 does work in the regular sine function, but is not an angle that works as an answer for the inverse sine. So what we have to do here, we have to think about what is an alternative angle that has the same value as sine of 115, sine of what angle has the same value, and does fall in that window. Does, for sine, fall between -90 and +90. So for this one, we'd have to realize, well, 115 would be in the second quadrant, so that would have a reference angle of 65 degrees, and that sine is positive in this quadrant. So therefore, sine of 115 is the same as sine of 65, and now 65 is in the window that we want, so this answer is just 65 degrees. Last little annoying aspect. I'm still going to keep saying evaluate, but this idea, we see it doesn't always cancel it perfectly. It needs that x to be in the right window. And that window, well, it depends what's on the inside. Is the angle in the right window? Is the value in the right window? So that's what we have to think about in order to make these cancellations, and if they're not, to make these final decisions. But these last couple of problems are something else. We're still evaluating. And let's take a look. Let's start a little nicer. I'm certainly not saying this is an easy problem, but just a little bit nicer. Let's take a look at sine of inverse tangent of 12/5. Okay, these do not cancel. You know, they're kind of similar in that one is a regular trig and one is an inverse trig, but they're different trig. So this is kind of like saying squaring and the cube root. Well, the cube root and a cube are inverses, and squaring and square root have ideas of inverse in them. But cubing and square roots, that's just not, that's apples and oranges. And that's what's happening here as well. So one more time, calculators help, but you often get ugly decimals, and this would be a spot where I would definitely want exact answers. So the best way to think about this is to realize we don't actually care what theta is. But that's the key. This is some angle theta. I don't really care about that angle theta. I care what is sine of that angle theta. That's the key here. And this, all of a sudden, this really goes back to some, how do I want to phrase this? Problems that we've seen very early. This is basically giving you a trig value and asking you for a different one. That inverse tan of 12/5 equals theta is the same thing as saying tangent of theta equals 12/5. So, if you know tangent of theta is 12/5 and you want sine of theta, we'd make a right triangle. I get to make the right triangle. I keep saying that in my previous videos, so I'm a creature of habit. I stick my theta in the bottom right corner, so my opposite, adjacent, and hypotenuse. Well, I know tangent, so 12 is the opposite side. A, the adjacent, would be the 5. I need the hypotenuse. I do a little Pythagorean theorem. 12 squared plus 5 squared equals h squared. I'd end up with a really nice clean 13 as h. And now, typically when we had these problems earlier, we try and get all the trig functions after this, but here all I need is sine. So what is sine? Opposite over hypotenuse. Our final answer would be 12/13. Now, I put a lot of little extra notes here. Some people do a little more work in their head, but that's the way to think about it. You do this work in the calculator and you get a very ugly decimal. Well, at least you could convert that decimal to a fraction. Most calculators can handle that, but that's the better way. Okay, and now let's do one more, and it'll look a little worse, but it's really the exact same idea. Let's take a look at secant of inverse sine of, let's do 3/4. Okay, this relationship I'm showing you here, when these don't match, this really relies on the inverse trig being on the inside, so we can do the same procedure. By looking at inverse sine of 3/4, well, I would know sine of theta equals 3/4, and this problem has really become, what does secant of theta equal? And I'm going to do it the exact same way. Again, I could write a little more out. You know, I could keep connecting the dots that this is theta, so that sine of theta is what I want. So this is theta, so secant of theta is what I want. Just writing it slightly different, I'm still making that same point. I know this about theta. I want to know this about theta. So use this fact. This time we know about sine. Again, I draw my same right triangle, but this time it's sine, so the opposite is 3, and the hypotenuse is 4. Here I labeled OAH, here I'm not. You do what you need to, everybody. If that helps, make sure you do it. It's a simple thing, just to make sure we don't have any goofs, filling values in the wrong spots, getting the wrong values. So here we are. I need this side, Pythagorean theorem, but this time it's 3 squared plus blank squared equals 4 squared. Again, another reminder, it's very common what people are missing to put that as the side by itself, but this is one of the legs. So either 3 squared plus blank squared or blank squared plus 3 squared, but the 4 squared has to be by itself. This does not work out so clean. Here you get a clean 169 is h squared. The square root of 169 is 13. Here we get 9 plus blank squared equals 16. So blank squared equals 7. We don't want our calculators here. We just want to leave that as the square root of 7. And now let's finish this off. The second little aspect here, at the end, you only wanted sine. Sine is one of our primaries. Here you want secant. Well, how do we get secant? Let's find cosine first. Cosine will connect us to secant. So I started with sine. Now I can find cosine. So cosine of theta would be adjacent over hypotenuse. And therefore, secant of theta would be 1 over this. So 4 over radical 7. I'm happy with that as an answer. But as we've said before, The book will always rationalize if it ends up with that radical on the bottom. So that would be the book's final answer.